Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to introduce Professor Ahmed Bouajani to you. Ahmed is visiting us for 4 weeks, and this is his second or third week? Second week. He's going to be here for another 2 weeks. Ahmed is a professor at the University of Paris, number 7, or Diderot, as they call it. He's interested, he has worked for many years on various aspects of program verification and automata theory and logics. And he has developed many techniques over the years on symbolic verification of infinite state systems. And I guess he's going to give a survey of that topic today. All right.
Yes, thank you very much. So thank you also for the invitation to here. I'm very happy to be here for this weeks. And so Shaz asked me to give a kind of overview on. So maybe I will talk also in the same time in the phone, or what shall I do here?
Ignore mute. Is that a mute?
Mute. Okay. Yeah. Okay.
Apologies for that.
Oh. Okay, thanks. So I will try to give a kind of overview, and in the same time also to show what are the current problems or research directions that we are trying to develop, and hopefully this also can show some links with what people are doing here, and I would be very happy to, of course, to discuss with you on these things during my stay here. Okay, so as just said, we were working on infinite state systems for now something like maybe 15 years. And there are many aspects in infinite state systems. So, of course, they appear, for instance, whenever you consider, for instance, timing constraints, those were maybe one of the first aspects that people considered in automatic verification, for instance, the verification of timing automata. And then you have other aspects like communication through unbounded queues. You have also aspects like recursive procedure calls for when you want to verify programs. You have also dynamic creation or deletion of parallel processes. You have also, for instance, the things related to data. For instance, the fact that a program can manipulate variables ranging over infinite data domains like integers and so on. You can also have things like sequence numbers, process IDs, announces, and things like that you can also that you want to handle, and also more complicated aspects like dynamic data structures, such as, of course, stack queues, but you can have also linked structures like doubly linked lists, trees, and so on. So in this kind of systems, so you have an infinite number of reachable states from a given initial state. And you have also something called parametrized systems. So often we combine, we mix these two notions, but actually there is a small difference between these things, is that here every instance of the system is finite, but you have to reason about an infinite number of instances. So here you have to prove that something is correct for an infinite number of finite instances. Okay, technically, for the verification of this class of systems, the techniques are very similar to the one that you use when you have some kind of dynamic systems where you have, from a given initial state, an infinite number of reachable states. Here, from a given state, you have only a finite number of states which are reachable. This can have some importance, for instance, for checking liveness properties. But okay, in this talk, of course, I will not go to many details, technical details. I'm just trying to give a general picture. Also, I mentioned that here, for instance, for parameterized systems, when we talk about parameterized systems, this is the parametric networks of systems. We may also consider other kind of parameterizations like bounds on the range of counters or timers, sizes of data structures, and so on. And the problems that you want to solve is that something is correct for all values of the parameters, or sometimes you want to synthesize the constraints. For instance, if these things are integers, you want to have some constraints which ensure that some system is correct. Okay? So in general, so you have to consider several issues. First, what are the suitable models for your programs or systems? And basically, we consider extended transition systems or rewrite systems. So of course, these two kind of styles of modeling are very related. So for instance, there are things like pushdown systems, which are automata extended with stacks. You can also have FIFO channel systems, clock systems, and so on. And you can also use some classes of rewrite system to model, for instance, as I will show, for instance, to model parameterized or dynamic systems and so on. So then we have the problem of specification, and there we have to come up with some formalism, which is either logic or automata based, which allows you to describe infinite set of configurations or states. So, and actually it's you have two issues here. You can use this kind of things to reason about infinite set of configurations, but you can also use these things to reason about infinite sequences of configurations. So you have kind of two dimensions, and both of them can be infinite. So you need some logics or automata which allows you to reason on that. And then, of course, you need also some verification techniques. And one of the issues that we try to address is to find algorithms which allows you to solve precisely, to decide that some model satisfies some specification. And this is for some specific classes of models. So you need some properties, because in general, if you consider general models, I mean, they are very often Turing powerful, and most of the interesting things are indecidable. So, but for some reasonable classes of models, then you can show that it's decidable, and you can get some reasonable algorithms. And also, we try to develop some generic algorithmic approaches, which allows you to handle, in general, some classes of models, and these techniques are not specific to some class of models, but can be used for a family of models. They can be precise, or they can be also approximate. So, and either give you upper approximations or under approximations. And we try to develop, again, some automata or logic-based formalisms, which allows you to reason about this infinite state of paths or infinite state of sequence of states. And here we try to develop some reachability analysis techniques, or for some cases, we consider only the problem of invariant checking. This means that if given an invariant, whether you are able to check that this invariant holds. Okay, so this is the general picture. And now, so let's start by simple things. So let's consider first symbolic reachability analysis. So here the problem is, given a set of configuration, you want to compute the set of reachable states, either forward or backward. Okay, so this is what we denote post-star or pre-star. So obviously here there is a basic algorithm here that everybody knows. So you compute a sequence of sets starting from S, and then you repeat the application of the post or pre transformation until you get you stabilize. Well, of course, this basic algorithm is very naive, but okay. So this is the, let's say, the basic schema. Already for this, you need some symbolic representation for these sets because they may be infinite. So at least what you require is some closure properties under unions because you are performing this kind of operations, and also post or pre. And you need also to be able to decide inclusions or emptiness and emptiness problems, okay? Of course. So those are the minimal requirements. And of course, how about termination? So this is, of course, also the crucial problem. So there are several ways of addressing this question. The first one is to say, okay, let's see if there are some general principle which allows you to prove termination of this basic algorithm that we have seen. So is it possible to have some schema for proving termination of this algorithm? So there is a theory, a nice theory, and actually very simple when you think about it. It's based on the concepts of well quasi-ordering. What is this? So a well quasi-ordering is an ordering which satisfies this property, that whenever you consider a sequence of configurations, say that we have here states, configurations, then eventually there exist 2 points, I and j, such that these 2 configurations are comparable. Okay? So this means that so you cannot have a kind of infinite descending chain. Okay? So, and this property ensures that, well, if you have an infinite number, of course, I mean, if you take a set of states, an infinite set of states, he will have only a finite number of minimals. Okay, and this is because of this property. You cannot have an infinite number of minimals.
Ahmed,
sure.
J is not bound in that definition.
What?
J is not bound in that definition.
No. This is an infinite sequence.
Okay.
So if you consider this infinite sequence, there is eventually 2 points in this sequence, I and j, such that these elements at this satisfies this property. Okay. So if you, for instance, you are looking at a sequence of states, of configurations, eventually you will find something which is bigger than something which has been seen before in this ordering.
So it's not for all I there exists a chain such that
No. Eventually you will, yes.
Eventually I'll find a pair such that...
Exactly. Eventually you will find a pair.
so just finding one pair is sufficient.
Sorry?
Just finding one pair is sufficient. Like
This means that you cannot have. I mean, you can always have. Yeah, for all sequences, yes, you will find some. So you cannot have an infinite sequence where there is nothing which is comparable.
Oh, I see.
Yes.
For
Okay.
example, this does not mean that if you have an infinite sequence like this, you will find an ascending chain in this sequence. It doesn't mean that, right? That's too strong.
No, that's too strong. Yes.
So, for example, if you had an infinite set of minimals, you just take that sequence of minimals
That's right.
and evaluate the property, right? So you cannot
Yeah, but you don't have. I mean, the fact that you have this means that you cannot have an infinite number of minimals. Yes. Yes, you have.
So this implies that there exists, each set has a finite number of minimals in the
Exactly.
application.
Yeah.
Even so, there could be infinitely many sequences. For each of them,
Yeah.
you have that.
Yes.
There's not like a diagonalization principle that I mean, how do you prove that basically there's a finite number of minimals? It's a simple proof or it's complicated?
Yeah, you take the infinite set of minimals.
Yeah.
It's just a chain. It values the property that exists one smaller than the other.
Say that again, please.
So take the infinite set
Right.
of minimals
Right.
and violates the property that there exists an I smaller than j. So that's says
They will be comparable. You see, I mean, this infinite, this property will make that you violate the fact that they are all minimals, right? Okay. So I mean, this is one consequence. And now, if you are interested about upward closed sets, So upward closed means that whenever you have some element in the set, you have all the elements which are bigger. So then actually you can characterize this set with only their minimals, because if you have the minimal, then you have it gives you all the information about the whole set, and you know that these minimals are finite. So you can use these finite minimals as a representations for these sets. Okay. So of course this is a very abstract things, but now in practice you have to have representations in some sense, and the effective ways of computing these minimals, if I give you a set, and also if I do the pre-computation, you have also to be able to compute it effectively. Okay, but if you are able to do that, then it's okay, because the other so that's that just a definition of this notion. Now, if your system is monotonic, and which means that this ordering on configurations is a simulation relation, which means that whenever you can do a transition from some configuration to another one, then if you take a configuration which is bigger than this one, you are able also to do some transition to another configuration which is also related to this one. So this is simulation relation, right? Okay, so if you have this monotonicity, so then you can prove, it's very easy, that the pre and pre-star images of upward closed sets are still upward closed sets. Okay, and if you prove that, so then you have a reachability analysis, because given an upward closed set, so now if this is your target, you can compute backward, and you know that it will always give you upward closed sets. Okay, and so eventually you will terminate. Why? Because you know that the image pre-star is also upward closed sets, so it's characterizable by a finite number of elements. So it's enough to collect these finite elements, and you will terminate. Okay, so you don't know when, but it will it will terminate, right? Okay, so and those are particular instances of this schema. So if you take Petri nets, and you are interested in this coverability problem, of course, this is reachability of an upward closed set. So if you want to say just whether there exists some token in this place, or there are two tokens in these places, or I don't know, something like that. So this is an upward closed set. So if you want to see if there is a possibility to reach such a set of configurations, so you can apply this schema, because you can here use just the ordering on integers, and you use the fact that Petri nets, you stay in positive integers. So you see you cannot go down. So if you go down, you can you see, you will hit zero. So you have to go up at some point. Now, if you take lossy FIFO channels, you take the subword relation. And this is something there is somebody called Higman who has shown that this is a well quasi-ordering. Okay, and there is a whole theory on well quasi-ordering. How do you compose well quasi-orderings? Giving well quasi-ordering, you can take product, you can take subwords on these things, multi-sets of things, and this is useful to build well quasi-ordering and to prove that some systems or some models are decidable using this schema. So this is a general schema. Okay. All right. Okay. So that is nice when you are able to have these properties, well quasi-ordering and show monotonicity. Now, in general, this is not the case. So another approach is to use the so-called accelerations. So here the idea is that if I give you a transition relation of your system, so assume that you are able to decompose it in some way. So of course, how do you do this? That's another story. But this is a general schema. If you are able to decompose it, so imagine that these things are, for instance, loops or some piece of your control graph somehow. And suppose that for these guys, you are able to compute the star. Of course, here you are trying to solve also the star problem. But you know that you can do it for simple relations. So you can use this knowledge to compute something for a more general relation. So you say, okay, now you take this basic schema and say, okay, now instead of computing the image by R of xi, I take xi plus the image by stars of these relations of xi, and there is some residual relation. Here it's R star. Okay, sorry, this is a typo. Okay, some residual relation that I don't know what to do with it, but I will just apply it and see what happens. Okay, but at least for these guys, I will go faster. And this is the concept of meta transition. I think the first time it was called meta transition is in some paper by Pierre Volper, and I don't know whether maybe you and Boisgelot, I don't know, Bernard Boisgelot or something. Yes. So, but this is the idea. And now, of course, here, termination is not guaranteed. Because doing just this will not guarantee termination in general. But it helps a lot. In many cases, it helps to terminate. Because you go faster to the limit.
How do you deal with that R prime star?
How do you do it?
No, the R prime, the residual part. How do you deal with that?
No, that's just you apply it. I mean, I give you a relation. Instead of just applying R to xi, so you say, okay, at least for this piece of this part of the relation, I can do better. And this part, I don't know how to do it. Okay, so just apply it once. But I will iterate. Okay? But these parts which are here, maybe they will compute fast some space of configuration which will make the whole things will converge. Even if this guy do something, it will be already covered by these things that you have done here. So, but in general, you cannot prove. Yes?
Is the intuition here that if you have one of the processes which performs some independent tasks of the rest of the world,
yeah.
So those are all grouped in one of these relations, and you can do them in one step, and then not worry about interaction with the other.
Yeah, that's one possible application to this. Yes, actually, this is somehow also related to what I am saying here, because in some sense if you are able, so assume that you have parallel processes as you said, and some pieces are completely independent, and if you are able to analyze these guys independently, so you can say, okay, I analyze in one step this one, and then see what he will do, okay, some kind of summarization of all what he will do, can give it to the other one, he will do the whole stuff, and so on. And this is very close to this bounded context switch analysis that, for instance, Shaz is doing. But in general, you can just take this schema and iterate now. Here you can bound this I. And if you bound this I, and you instantiate this schema, this R star, with what you were saying, this is the bounded context switch. Because you bound the number of the whole iterations, but each iteration is an acceleration step, okay, locally. But you can apply this in more general, things that just for this. Okay, so in general, you can use this bounded accelerated iteration for under-approximation analysis. Of course, for the things for which you know how to do these R stars. And there is, so those are just some references on works that exist, for instance, for counter systems, functional systems. So you see that Boisgelot, Volper, and people from Uppsala and Cachan has done a lot of things about these classes of systems. Now, the other approach is to say, okay, I don't want to do a precise analysis, I want to do abstraction. So this is very well known. This is abstract interpretation, or inspired from abstract interpretation. So you say, okay, I take this basic schema, but I introduce here some abstraction, so which will upper approximate. So now there are several cases. Still, you can prove termination of this one. If you have a finite range, this means that your abstraction here can have only a finite number of possible images, or something more general, that you can use this well quasi-ordering business to show that actually you are iterating in some space where you have a well quasi-ordering, and then you will terminate. Okay? Now, in some cases, it happens that you can have a precise analysis. And those are just small examples. Actually, when you look at the proofs which are here, you can phrase them as a schema like this where you have some abstraction. I mean, if you take timed systems, this is, of course, you partition the state space in some way, and you show that this partition gives you precisely the whole information about your system. And if you look at the construction of pushdown systems that we have in this paper, so actually here the representation is a finite state automaton for the contents of the stacks. If you do one pre-computation, this construction introduces some new states, which are the initial states. So you see, if you keep iterating this pre-computation, you will never terminate. And what we had as an idea is very simple. So just collapse all these initial states, put them together. So this is kind of equivalence relation that you define on the states of this automata. And it turns out that this abstraction is correct. We prove that this is correct, and this means that you are computing precisely the image. So, and of course, in general, this will not be precise, but there are many techniques for refining abstractions and so on to get it more and more precise. This is like the CIGAR approaches and all that. Okay. Now, there is something called regular model checking, which is something to do symbolic reachability analysis using automata. So this is a kind of generic framework where, so it was developed by a lot of people here. Okay, so you see some names here. And the idea is that just you take a configuration of your system and try to encode it as a word. And then sometimes you use also trees, but okay, let's consider just words. So first you try to encode configurations as words, and then naturally you can represent set of configurations as finite state automata, and then actions also can be represented as automata, which are called transducers. So these automata are input-output. They read the input and they produce the output. Okay, so they represent the relation, the transformation between configurations, before and after. Okay? So now, how do you phrase the reachability problem? Is that given an automaton, this is the initial states, and a transducer, so you apply iteratively this transducer to this one. So T star is the transitive closure, reflexive transitive closure of the relation represented by this T. And you intersect it with another B, and you check for emptiness. So all these operations for finite state automata are doable using basic algorithm. Of course, the main problem is how do you compute T star? Again, I mean, there is no miracles. But it just you rephrase the whole stuff in the framework of automata. But now you have a representation, and you can now work on this automata and try to define some generic algorithms for how do you compute these T stars. Okay? And actually this was, this is what all these people were doing during, yes?
So Ahmed, can you go back one slide? So would you say that symbolic model checking using BDDs
This is a special case.
It is a particular case of this, right?
Well, okay, so theoretically, yes. The BDDs, the interest of BDDs is more because you can implement them efficiently using this cache and all that. Okay? So, that makes them, useful in practice. It's not the fact that they are special cases of automata. I mean, if you just say this, it's all right. But now you need something more, because on this particular case, you are able to have specific implementations which makes the operations efficient. For automata, you have also some properties like in BDDs. You have canonicity. You can have this deterministic minimal automata. But it's difficult, for instance, to develop techniques where you have this cache, because you want to somehow memorize some pieces of automata and so on, and reuse them later and so on. Right. So there you have to reason about the structures of the automata and so on. You see, the difference is that BDDs are acyclic automata. So it's easy to build them top-down in some sense, or bottom-up, sorry.
But I mean, the reason I wanted to point out this connection is that in any problem, there's going to be a Boolean component of the state space. And then there's going to be some other unbounded crap that you need, like all this automata power for.
Right.
Right? And I mean, because you don't want to just throw out, so we know that for Booleans, okay, to some extent BDDs provide a good representation. And maybe that's sort of the bulk of what you need to do. But then you need some extra stuff on top of it for representing these things. So maybe one way to think about the problem is that you already have BDDs to represent the Boolean component, and then you add some extra stuff on top of it, right?
I mean, we were thinking about things in this direction, but I think this is still an open question. How do you combine different encodings? Because you have different encodings of different representations. You see here, one of the problems is to come up with this encoding. And for instance, even for integers, so the basic idea for encoding integers is to consider them as, you encode them in binary. And there are automata which are based on this idea, so developed, for instance, in Liège and also in Cachan and so on. This is, but the problem is that
the variable ordering and all that.
Yeah,
exactly.
You have also this problem. Yes, of course. Yeah. But now if you mix, for instance, you have integers plus, I don't know, Qs. So what is the good encodings? How these encodings interact? How are you going to, whether you will encode this configuration sequentially, whether you will shuffle these encodings? It's not clear. So that's a real problem. How do you come with representations for different data structures, and how do you combine them? I think that nobody knows how to do this.
Right.
Okay. Yeah. Okay. So, but this is an important issue. I agree. But I still have a lot of to see. Okay. But we can talk about it because yes, there are some ideas on how to do this, but I don't know. It's not clear what is the good idea there. Okay. So here, just mention that there are different ways of attacking this problem here. One of them, actually, it follows this schema that I presented before. You can use acceleration techniques for some special relations. You can do some generic computations of this T star using some abstraction on the transducers. Here you are computing transducers iteratively, but you want to come up with some kind of principle of collapsing this transducer to make the state space of these transducers finite and terminate. But you want to be exact in order to compute precisely T star. So those are some techniques that, for instance, were developed in Sweden. And then what we have done here, for instance, in Paris, with collaboration with Brno University, is to use abstractions on the automata, to collapse automata, and this abstraction can be refined. And this is, in some sense, more efficient in these things because at least it gives you some regular abstraction of the image that you want to compute, even if this image is not regular in general, because that's one of the problems, that in general this T star of A is even not representable, the precise image, by finite state automata. But if you use abstractions, you can come with some regular abstraction, which is an approximation of the real image. And this could be good enough to prove that's, your reachability problem. Okay? And this
or you can just ignore that issue and just do finite unrolling of T.
Of course.
Find bugs.
Yeah, that's the other approach. Yes, either you do abstractions or you do finite. Yeah. Yes, sure. Okay, now currently, so of course, I mean, these techniques have different problems. One of the issues is the encodings. I mean, how to find efficient encodings, and you have to reason about the structural properties of these encodings and so on. And you have also to use, I mean, if you want to use abstractions and so on, that's a problem. Another idea that we try to now to see whether it will be interesting to, and it seems very promising, is instead of using canonical, this minimal deterministic automata, is to use non-deterministic automata. And it turns out that's because, I mean, in many cases, non-deterministic representations of a language is much more compact than the canonical one. And also, you don't need to do this determinization step, which is, I mean, which can make the automaton blow up before that you minimize it. So then for that, you need two ingredients. How do you check inclusion? And this we use, there are these techniques called anti-chains, which have been introduced in this paper, and we are trying to develop them here. And there are also other ideas on how, because that one thing is how do you check inclusion. The other thing is that you want to make the representation always small. So then you want to minimize. So of course you want to minimize with respect to language, trace language equivalence. But this is, of course, difficult because you want to do determinization for that. So what we try to have is some kind of simulation-based relations. Of course, so you can minimize according to simulation equivalence. But actually, even this is too strong. So you can find something which are between simulation and trace equivalence. And they give you better reductions, okay? And this is what we try to develop here with the team of Sweden and also with people from Brno. Actually, the idea is very simple. I can show you the basic idea is that you see, I mean, what you want is to collapse two states. Instead of saying that these two guys should be equivalent, what you want is that you want to collapse these guys without introducing bad sequences in your automaton. So what you want is that if I take some past trace from here and some future trace from here, when I collapse these guys, this new trace I will create is also in the language. Okay? And so for that, I mean, we use some equivalence which use combinations of forward and backward simulations. Okay, and we have also some idea to make these things. So the idea is to have some polynomial algorithms for checking these equivalences, and which gives you equivalences which are coarser than simulation and which are still compatible with trace equivalence. Okay, so that's one direction. And actually, it's interesting to see that there is a lot of activity now recently about this, how to find efficient algorithms for simulation relations. There are a lot of people working on this algorithm. I mean, very recent development, interesting algorithm. I mean, I think that there is still a lot of work on the algorithmics of these things. How do you do it? Yes?
So for all these, the goal is to preserve perfectly the language.
No.
No, you allow...
No, this is just from the point of view of automata. It has not, you want to preserve language when you minimize.
Right.
Okay, yes, in these things, right.
Not the last bullet is abstraction technique.
No.
There you allow
No.
approximation.
Yes.
So then if you allow approximation, it's easier.
Good question. Yes. No, but there are two steps. But you are right in some sense. Because when these things are somehow independent on which kind of analysis you want to do. This is kind of problems on automata. How do you check inclusions efficiently? How do you minimize them efficiently, and so on. So that has its own interest. Now, when you do symbolic analysis, so you can use these things, But I agree with you because if you are interested in abstractions on automata, maybe you don't want also to do these checks in precise way. You can also have some safe way of checking inclusions and safe way of, you see, okay. And in that case, yes, you can even go, you can have even better performances. Right.
This work has also been applied to, let's say, alternating simulation and looking at open system analysis, where you would look at simulation as sort of a game, have a game view on the system behavior. Do you know if I just noticed Hansinger's name, so he has been, for example, applying this, if one could apply this to interface automata.
Right. So here, in this paper, they were looking at word automata. They have developed, I think, something, but so in this paper we were considering also tree automata. This kind of things we were generalizing to trees, and in this simulation business it's also the case that you can consider either the word case or tree case. The tree
case is somewhat related to alternating.
Exactly. That's why I mentioned this. Is that you can generalize this kind of concepts to trees. Here the idea will become a bit more complicated because in trees, you see, you have the context somehow. You have to what is called forward will be something which looks at the tree forward, and what is backward, you look at the context where you plug this tree. So it's a bit more complicated, but the same kind of idea you can use. Yeah. Okay, so now I think I have to watch my so okay, so if we come back to the modeling now, if we look at so this was about this generic frameworks. Now if you look at for parameterized networks, what can be done? So a simple case where the most simple case still is not very simple is when you have what's the so-called unstructured networks. This means that you don't care about the IDs of the processes. So some process will communicate with some other process, but he is not able to say that I'm communicating with process number I plus 1. I am number I and I want to communicate with my neighbor, for instance, or something. He's just communicating with somebody. Okay? And if you have a finite number of variables and so on, so then a natural model is Petri nets. And the idea is that what you are interested in is to count for every state how many processes are currently at that state. Okay, and now if you see any transition can be encoded as decrementing this counter, because one process is moving from this state and going to another state, so you increment the other counter and so on. So this is very natural. And then if you want to solve control point reachability, this is reducible to upward closed set reachability, and this can be then reduced to coverability problem, and we have seen that this can be done. And you can of course extend this. You can have broadcast communication, and for that you use what is called transfer arcs in Petri nets. This will you still can apply the same principles, and of course dynamic creation is not a problem because in Petri nets you can create tokens, and this has been actually applied in this paper for the verification of multi-threaded programs. So they show, for instance, that you can take Java programs and you can translate them systematically to this Petri nets, and then you can use analysis. And okay. Now, if you care a bit about the identities and assume that you have an ordering between these IDs, so you have linear topology. Now, it depends on how do you deal with these IDs. You can have different topologies. So, for that, what can be done is that you can use now this regular model checking to model these configurations and transitions. So if you have an ordering, then this means that you take a sequence, and at each position you have the control state of one of the processes. Okay? And now if you want to say that, okay, so here, for instance, I have something which will give the token to the neighbor. So this means that this guy is doing I send the token to my neighbor, so this just can be encoded like this. This guy has 0. Okay, so this is this is a transducer. Okay, I hope that you can understand these notations. This means that I don't have the first. Okay, in the configuration, so I have only zeros, and somebody has 1. Okay, and then you have zeros, and this is the token. This is the process who has token. So you want to give the token to this guy, and or maybe in the other way. It goes this way. Okay, so you want here to exchange this information. Okay, so this is kind of rewrite step. So you say that if I read this sequence with 0, 1, I have to replace it with 1, 0. And this is what is shown here. Okay? Now, if I have in this one, so you can say that, if I am process I, if my state is B, and all the guys before me have A, then I will move also to A. Okay? So again, you can encode it this way. So this is very simple. And now you can use this regular model checking techniques that I was talking about to compute the transitive closure and so on. And of course here, the main problem is the encodings. Given a protocol, for instance, how do you come with these transducers which encode the actions and so on? So sometimes it's not it's not trivial. Yes. Okay. So now, here, for the moment, I have considered only the fact that the processes, you have networks of processes, but they have a finite number. Their data are in some finite domain. Now, it could be possible also that you want to consider networks of systems where you have infinite. Each process is itself an infinite state system. So you may have, for instance, a network of timed systems, like, for instance, if you have a Fisher protocol, this is a typical example. You may have a network of counter systems. For instance, if you look at bakery algorithm, each process has counters, and you have an arbitrary number of these guys. You can also have a network of pushdown systems. If you have, an arbitrary number of processes or of threads, each one has procedure calls and so on. So you will have to model it by a pushdown system, but you have a network of them and so on. So then you will have 2 dimensions of infinity. So how can you handle this? So I will talk a bit about this. I will not go to details. I will skip this part, and then I will try to say something about this. So for communicating pushdown systems, so here actually one of the ideas is to say, okay, if you have concurrency and procedure calls, basically maybe the models that you want is some kind of combination of Petri nets and pushdown systems. So we have seen that if you have finite state systems and you have a network of them, so you can model them as Petri nets. If you have just sequential programs with procedure calls, you have pushdown systems. If you have both aspects, so you have to combine these things in some sense. So this is very rough what I'm saying, but in fact, if you look at the models which are considered somehow, they all have this kind of things. So you have some kind of creation of processes, or you have some communication on these things. This is kind of Petri net model, but each process is itself a pushdown system. Now you have, of course, if you want to have some analysis to put some restrictions on the control or the communication primitives, how do you create processes, how do you make them communicate, and maybe the network topology, how this network is done. Of course, you know that if I take two pushdown systems and make them communicate in an arbitrary way, then the reachability problem is indecidable in general, of course. So here there is a lot of work which has been done recently on models which are based on this combination in some sense for different classes of systems. So you have these PA models which allows you to do this par begin, par end block. So it's very limited way of concurrency in some sense. There is no real communication, just that you can fork and you wait that this guy terminates, give you some result to continue. And this has been studied in many works here. And then there is this paper where we try to really to model dynamic creation of threads, because this is not really dynamic creation of threads. And here again the communication is restricted because a thread can create some number of processes, and it can check some condition on their states. So in some sense the children can give some information to their father, but it doesn't go the other way. So it's kind of unidirectional communication in some sense. But it's more general than this one, and again you can, for these things you can apply techniques based on automata like in this pushdown, but you generalize them here. It's a bit more complicated, but still using these things. Other models, for instance, has been considered recently, which somehow you have a pushdown plus a multi-set of pending tasks. So you create tasks, and they are waiting there till you can handle them. But so you can only handle them at under some specific conditions. You cannot, for instance, interrupt tasks and so on. And this has been shown to be decidable, and more recently there was some developments on how do you come with a more efficient procedure for this. Recently we have considered these models with task preemption. We have shown also that this model is decidable, but the complexity of, in some sense, will be of course at least as this one.
But as soon as you have task preemption, doesn't it become undecidable, because you have now a general, like two pushdown systems interacting with each other, right?
Yeah, but okay. So preemption here, what we mean is that, so when you create, so you have some priorities on tasks.
Okay.
And when you create a task with a higher priority, so you preempt the one you are dealing with now, and you start processing this one.
Oh, okay. So you still just need one stack. That's why it's decidable.
Yeah, but the complication comes from some other things. Is that when you start dealing with this higher priority, you will not resume these ones only if these guys, there is no one left. So there is a kind of test to zero. And if you add test to zero in Petri nets, it becomes dangerous. But we show that still this kind of tests to zero are in manageable somehow. Okay, so that's the difficulty. But still, yes, you have one stack, but the problem is how do you go from one level to another one, and you cannot come back only when you empty this one. And also, next week, Fauzi, who is this guy, Atig, will give a talk also on some pushdown systems with the lossy channels. Also, okay. And of course, this is when you care about exact analysis, but you can, in some sense, you have also some approximate analysis, like upper approximation using abstractions, or under approximation and using, for instance, this idea of bounded context switch and so on. And some of these results which are here can be used in some sense here. Okay. So that's
Oops. What happens? Okay. So now in if you want to consider a more general framework where you can have an unbounded number of processes of infinite state processes. So this is, for instance, the typical examples. I will not go to this. I think that everybody knows the bakery algorithm, but you know that here you have kind of an arbitrary number of processes, but each of them has some counters. Okay, so what happens? So here the idea is somehow what we try to do is to extend this framework of regular model checking in some sense in order to have this data. So regular model checking consider words or trees which are over a finite alphabet. So now if you have data, this means that you need to reason about infinite alphabets in some sense. So this means that instead of having words, you will have what we call data words. So each position in the word has some data attached to it. So for instance, in timed systems, you have timed words. So this is a particular case where you have some number of clock values attached to each position. Okay? But here you have something which is more general. You can have any data domain. So here in this work that I will present briefly, we will not consider reachability analysis. We just want to have some kind of post-pre-reasoning. So just we want to have some framework where we can check invariance given by some user. So you have models we consider as rewrite systems over data words. Okay, I think that you see that between these transducers and the rewrite system there is a close relation. So instead of, you could have also transducers, you can define them, but okay, it's more easy to use this kind of formalism. It's more simple to reason about it than automata in this case, but it could be defined. And then we try to define a logic for expressing constraints over these data words, and try to see whether there are some, what are the limits of the decidability, and we try to also give some algorithms for invariance checking. Okay. So data words. What is a data word? Is just like usual. You have a finite alphabet, which, for instance, represents some finite information. And you have a data domain, which is potentially infinite. And you have some number of values. So here there is this dimension n. So intuitively you have, for instance, n variables. So you have a vector of data which are attached to some position. So now your alphabet is just this set. There is some finite information given by this element in sigma and some vector of data values. So this is one element in this set. So you have the label and the data. Okay? And now we will consider words over this alphabet. Okay? Now, what we define is the data word logic. So what is this logic? Basically, it's a first order logic. So assume that, okay, forget about data for a moment. You know that in general, when you consider words, you can reason about words in first order logic where you quantify over the positions. You say there exists a position, so just for every position bigger than this one, something is labeled by A or something. Okay. Now we add on top of this something which talks also about the data. Okay. So this is a parameter of this logic. So, so given our data domain, and we consider some kind of first order logic on this data domain. So you have a set of functions, a set of relations. Okay, then we define, so what is a formula? So you can talk about those x and y's, talks about, those are positions in your word, so you can talk about the ordering.
you can talk about the label attached to this position. So this is this finite information. And this is some constraint on the data. Okay? So this is R, this is a relation in your first order logic on the data that you consider, and those are terms. So what is a term? A term can talk about, so this is a data value, okay, so this is a variable on data, sorry, and you could have, you can talk about the data attached to this position X, and this K is just to say that this is the kth element in the vector that you have, okay, because you have a vector of data domain. And this is, you use some operations on this data domain, so you can, you know, add, if you have integers, you have addition, multiplication, I don't know, I mean, could be anything. Okay, so this is to talk about the data. And this is, as usual, you'll have Boolean connectives, and this is first order quantification over the data variables and the position variables, okay? So now if you define this framework, so this is just the definition. So those are some examples. So assume that that data domain is Z, integers, operations are 0, 1 plus, relations I have ordering, and I have dimension 2. I have two elements. So I can write that for every position, if I have the label A, then there exists a position beyond this X, such that I have B, and then I have some relation between the values of the variables, okay, which are attached to this position, okay? Now you can, for instance, have express ordering. If for this you need only this theory, very simple. You can say that, for instance, all elements in the sequence are ordered, for instance. Okay. So this is the logic to talk about these words. And now how do you express the transformations? So we have rewrite systems. So rewrite systems are as usual. So you rewrite some positions which are labeled by A0, AN by some word which is labeled by B0, BM. And you have here some constraint which talks about the data which are attached to these places. Okay? So basically you say what are the values which are here and how they are related to the new values, and also maybe how these values are related to the context where they are in the word. Okay? So I think I will not go to details because we don't have time, but I hope if you have, if something is not clear, you can, of course, stop me. And you could also have different ways of policies of rewriting. You can consider that for a given rule, you can have what is called factor rewriting. This means that you take a word, and if you have this correspond to this left-hand side, so you can replace it by this right-hand side. But you can also consider prefix rewriting to model pushdown systems. You can have multiset rewriting for Petri nets. You could have also this. So those are different kind of policies of rewriting. You can define various things like that. So for instance, if I take this bakery algorithm, so this is kind of how do you model this transition relations. Okay, so you say that from if I am not in the critical section, I go to the position request, but I have to check some condition on the data, and from request to critical section, I have to check that this variable satisfies some condition. This is the usual constraint and so on, and this is the set of reachable, I mean, this is the set of initial states. You say that everybody is non the critical section, and mutual exclusion, that this means that so there are no two processes in the critical section. Now, what? Yes. Sorry. Yes.
A question about the model.
Yes. Yes.
So can you go back? Don't mind.
Yes.
Right. So here you want to specify using rewriting each of the concurrent processes or all of them together?
No. This is in this modeling, all of them together.
A trace which can be potentially produced by a concurrent.
No, it's not a trace. It's a configuration, and you define what is the step. So if one process can do something, So you just say that if I have a configuration, some guy is at some position with some configuration that is, and you can express it in this constraint, then I move to some other location.
Two guys can do something at the same time.
Yeah, but you can say it.
You have an adequacy result saying that something is possible in the original system, if and only if it is possible on this encoding.
No. Okay, so if you want to encode that two guys can do simultaneously something, so you have to say, I mean,
So they can just do it. If they want to update some local variable,
Yeah.
they can just do it concurrently.
Yes.
Right. So how about on the rewrite system on the Word?
Yeah, but that's what I'm saying is that okay.
I mean, you don't need to go into details.
But just to show you, there is this configuration. You want to say, assume for simply that they are neighbors, these two guys who will communicate. So you say that this was in A and this one is in B. I want to go to A prime and to B prime and transform the data somehow. Okay, so this is a rewrite rule of the form AB goes to AB B prime and some constraint here which tells you how this data has been modified. Okay? And this formula can also talk about how this guy occurs in. You can also specify this place and also how this data are related to the whole context. And you say how they are transformed. Okay? Now, if they are not neighbors, okay, I have not talked about it here, but you can do it in the same. I mean, you can.
One of the nice things of rewriting is that rewrite rules, if they do not overlap on the left-hand side, you can proceed concurrently. So I was wondering whether you capture by this concurrent application of rewrite rules the intended concurrency of
No.
encoding.
Okay, we don't have concurrent rewrite rules. I mean, this could be defined, but I mean, in what I'm saying here is that a rewrite rule just talks about the whole configuration of the system, how it's transformed. So if you want to talk about concurrency, you have also to encode it in here. But now you can imagine that other semantics of rewrite rules where you can have these parallel rewrite rules and so on. Okay, but this is not what I'm talking. Some of these aspects I will call at the end, something we call universal rewriting, because you want to say that I have to do this, but now whenever I see some other position labeled by C, all of them, I have to transform them to D, for instance. That's also something we can do. And this is, for instance, like this transfer in Petri nets. You want to take all those who are in some state and move them simultaneously to some place. And this, for instance, allows you to do broadcast communication or something. Okay? So that's kind of things. I think you can define different semantics for the rewrite systems and try to see if... something interesting is to see, I mean, whether there is... but I think we can define some kind of transducers which define all these kind of various patterns or something. I mean, yes. Okay. So let me just mention quickly the results here because we are running out of time. So what we can prove is that if this first order logic that you have on the data is decidable, then the fragment sigma star for all star, and those things talks about the positions. So this is decidable. Whenever this theory is decidable, this one is decidable. Okay, and this is done by by a reduction of the decidability of this, the satisfiability problem of this fragment to the satisfiability problem of this one. Okay, so it's based on some kind of small model property, and you can reduce this to this. Okay, so it's I'll not go to details. And something also interesting is that you cannot go beyond. I mean, if you take the complements of this fragment, so if you take this one, so it's indecidable even for very simple theories, even if you have equality or ordering. So that's indecidable. Okay? And we show also that you can compute post and pre-images. So this logic, this fragment existent for all is closed under this post and pre-computations. And this is for these policies that I was talking about, but maybe we can imagine other policies of rewriting and still this result can hold. Okay? So, okay. And this tells you as a corollary that if you have some, if your set of initial configurations is in sigma for all, your invariant property that you want to check that it's an inductive invariant is a Boolean combination of sigma formulas. So sigma and for all. I mean, you can have these things. Then you can check these two things. They are decidable because, okay, it's their direct consequence of these results that I was talking about before. And this can, for instance, in this example, you can see that you have this kind of, so because here you have this invariant, but it's not inductive, you have to come with this one. And then you can see that it's in this fragment that I have shown to be decidable, and it's okay. Now, so we have an implementation for the case of multi-set rewrite systems, but the same thing can be extended easily to the word case, and we are still working on this kind of things, and to extend to more general structures. And the satisfiability can be reduced to SMT solvers. So here we use this one, but actually we can use anyone which is connected to this Y platform. So I don't know if you know this one. It's developed in Paris. So they have some tool for program verification, but the things that we use here is that they have the connection. They have a language where you can write these constraints, and it's connected to many SMT solvers, and you can do this. And it works quite well. So and for instance, we have been able to do some examples like this one, which was, I think, in one of your papers, but here it was, we have done it in a parametric way and so on. Anyway. Okay.
Did you have to change the underlying solver to implement this?
No. I mean, the procedure we have just produce the constraints in the language of this Y.
So it's based on finite instantiation, right? So
yeah.
So when you express the program.
No, our program. So we have our program, okay. So then we apply our procedure decision, reduce, the check-in, for instance, some implication or something to the satisfiability problem in some data theory. And this one is in this written in this Y language, and then you can use any of these SMT solvers, Z3 or I don't know, things like that. Yeah. Okay. Now those are things that we are doing. So yes, so we have this universal rewriting that I mentioned before, and this is useful for timing constraint broadcast communication. For instance, you want to do this notify all modeling. And we have also extended this to nested data words. And so you can have kind of composite data structures. You can have words of words of words. For instance, if you have a multi-threaded program, you have several processes, but each one has a stack, and this stack contains integer data, for instance, some ID of something, or things like that. So then you use this nested modeling, and so this is a recent work that we have done. And we have also extended this to, we are also working on dynamic linked data structures in this framework. So for instance, we have also done something recent here on multi-linked lists. This means that you can have doubly linked lists, but you can have, several links going forward and backward. And you can have integer data in these things. And we have also combined these things with this one. In some sense, you can have several layers with the arbitrary data domains. And for trees, this is something like, we know that the logic is decidable, but we still have to work on pre-post computations and so on. So this is also something that we can do. And we want also to do invariant synthesis using this abstract symbolic reachability analysis. So actually, there are some people from Uppsala, Parosh, and the students who have done some symbolic reachability analysis in logics which are some kind of particular case of these things. We can try to use these things here. And we want also to develop some kind of Segar approach using predicates in this data structure logics and so on. So those are some references if you want. And I think I'm done. Sorry, it was too long, but...
Let's thank the speaker.
Yeah.